This is your presenter Asloob Mudassar, and I am presenting slide number 12D of the course on atomic and molecular physics. In the today's lecture, I shall be covering the following topics, that is fine structure in hydrogen atom, lamp shift and its measurement, H alpha line in the presence of a fine structure and lamp shift. This lecture, which is lecture number D, is in continuation of the previous three lectures. For example, the summary of the lecture which I presented in slide number 12A is here I have presented a relationship with the orbital magnetic moment and the orbital angular momentum of the electron given in equation number 13. Then this is another relationship in the presence of the GL parameter. In equation number 16, you can see that there is a GL parameter, and this is again a relationship in the vectorial form. Then the equation number 12 gives you the orbital magnetic moment of the electron in terms of the magnitude of the orbital angular momentum. This relationship that is in equation number 12, the relationship is in the form of the magnitudes, and then we have the z component of the orbital magnetic moment. If you take the z component of the angular momentum, then of course that z component is given by ml h bar, so h bar will be cancelled out and you are left with ml, where ml is the orbital magnetic quantum number. So this is the relationship in terms of the z component of the magnetic moment. And if you take the maximum value of the z component, then you need to take the maximum value on both sides as shown in equation number 18. So I am writing the maximum of the z component of the orbital angular momentum on the left hand side, and on the right hand side I have replaced ml with the orbital quantum number L, because the maximum value of the orbital magnetic moment is the orbital quantum number L. So this is actually the quantum number. So in equation number 18, on the right hand side you have the quantum number L, which is actually the maximum value of the orbital magnetic quantum number ML. Then in equation number 25 I have the expression where I have related the magnitude of the orbital angular momentum in terms of the quantum numbers. So L mod is equal to the square root of L into L plus 1, and outside that one I have H bar. Here on the right hand side the L represents the orbital quantum number. Then you can express the z component. You know that when you apply the magnetic field, the orbital angular momentum starts precessional motion about the magnetic field, which is the case of the pure orbital magnetism. So when the orbital angular momentum starts its precessional motion about the magnetic field, then of course there will be three components of the orbital angular momentum, which will be Lx, Ly, and Lz. The two components which are Lx and Ly components, they are averaged out to zero during the precessional motion, and only one component, which is the Lz component, will survive, which I have given in equation number 24. So Lz is equal to ml into h bar, where Lz is the z component of the angular momentum, that is the component in the direction of the magnetic field, and ml is the orbital magnetic quantum number. So the allowed values of ml are from 0, plus minus 1, plus minus 2, plus minus 3, and so on up to plus minus L. That is, ml will have a maximum value equal to either plus L or minus L. So ml is the magnetic quantum number. This was covered in lecture number 12A. Now the summary of the lecture number 12B is defined here. In the lecture number 12A, I have discussed the orbital things. Now in lecture number 12B, I am going to discuss the spin things. That is the quantities related with the spin angular momentum and the spin magnetic moment. Equation number 29 here represents the absolute value of the spin angular momentum in terms of the spin quantum number. So the mod of spin angular momentum is equal to the square root of s into s plus 1 into h bar, where s on the right hand side is the spin angular moment, is the spin quantum number. And you know that for the case of a single electron, the value of the spin quantum number is always half. So s will be equal to half for the case of single electron. Now this relationship in equation number 30, I have the relationship in terms of the spin magnetic moment mu s in the vectorial form written on the left hand side, which is equal to minus gs into e over 2 m naught into vector s. This vector s is actually the spin angular momentum. So here in equation number 30, I have the relationship of the spin magnetic moment relating with the spin angular momentum of the electron, and this is the vectorial form of the relationship. Then again, if you want to write the z component of that one, whenever we talk about the z component, it means that we are going to apply external uniform magnetic field to the atom, and in the presence of the pure spin magnetism, the electron, the spin angular momentum of the electron and as well as the spin magnetic moment of the electron will start precessional motion about the magnetic field, and then of course the three components will be generated: Sx, Sy, and Sz. The two components Sx and Sy will be averaged out to zero during the precessional motion of the spin angular momentum about the magnetic field, and only one component will survive, which will be the Z component. So Sz will be equal to Ms into h bar, where Ms is the spin magnetic quantum number. So Ms is the spin magnetic quantum number, and it has only two possible values. Ms is equal to plus minus half, which is written below. So ms equal to plus ms is equal to plus minus half are the two allowed values. So this sz, so sz component and ms values are shown in equation number 1230. Now, if you take the z component, of the spin magnetic moment, you need to take the z component on both sides. So, in equation number 32, I have mu sz written on the left hand side and is equal to minus gs into mu b into ms. And you know that ms is actually written, which is the spin magnetic quantum number. And this is because I have taken the z component of that one, and the z component is sz is equal to ms into h bar, which I have replaced over here. So in equation number 30, the sz component of s has been replaced by ms into h bar in equation number 32, and then of course after necessary cancellation I have written down this relationship. Now there are two values of the gyromagnetic ratios. One is the orbital gyromagnetic ratio, gamma L is equal to GL into mu B over H bar, written in equation number 37. And then we have the gyromagnetic ratio, spin gyromagnetic ratio, written in equation number 38. Gamma S is equal to GS into mu B over H bar. And you know that mu B is the Bohr magneton. So these are the quantities which are spin related. Now these quantities can be measured. For example, the gyromagnetic ratios by Einstein-de Haas method. So mu s and mu l are associated. In this experiment, it was established that the spin magnetic moment and the orbital magnetic moment, respectively labeled as mu s and mu l, are associated with the spin angular momentum s and with the orbital angular momentum l of the electrons. So these quantities do actually exist. Then the detection of the directional quantization was presented by the Stern and Gerlach experiment, in which it was established that mu, which is the magnetic moment of the electron, it could be a sum of, or the vectorial sum of the mu s and mu l. So mu this mu can be measured, and it has a directional quantization. So in this experiment by Stern and Kerlock experiment, it was established that there is a quantity which we know as the magnetic moment of the atom or the electron. They are this quantity do exist, and it has a directional quantization under the application of the applied magnetic field. Then you know that when we apply the constant magnetic field, then of course there will be a precessional motion of these four quantities. That is the orbital angular momentum L, spin angular momentum S, orbital magnetic momentum mu L, and the spin magnetic momentum mu S. These four quantities will carry out precessional motion about the external magnetic field. These topics have been discussed in much greater detail in slide number 12D. And in slide number 12, see that in lecture number 3 of the in lecture number 3, which is continuation of the previous two lectures, the following things were presented. So J, that is the total angular momentum of the electron, is actually the vectorial sum of the orbital angular momentum and the spin angular momentum. So J is equal to L plus minus S, as shown in equation number 48 will be valid. And remember that J is actually now the total angular momentum of the electron or the atom. Then in magnitude form, the equation number 48 can be written as shown in equation number 49a. So J mod is equal to mod of L plus minus S. And in terms of the quantum numbers, I have written this relationship shown in equation number 49b. J is equal to mod of L plus minus S. This relationship is in terms of the quantum numbers. J is the total quantum number of the system, L is the orbital quantum number, and S is the spin quantum number. For the case of single electron, the value of S will be equal to half. So for S electron, L will be equal to 0. For P electron, L is equal to 1. For D electron, L is equal to 2, and so on. So these quantum numbers can take these values. Now the selection rule which will be applicable to the quantum number J will be equal to delta J is equal to 0 plus minus 1. So these are the allowed values for the optical transitions. Optical transitions are the transitions which are called radiative transitions, in which a wavelength is emitted. And then you see that J in terms of the magnitude, that is the magnitude of the total angular momentum of the electron or the atom, is written in equation number 50, which is J mod is equal to the square root of J into J plus 1. Outside that one, there is H bar. And this J on the right hand side is the quantum number, is the total quantum number of the atom, whereas J mod written on the left hand side of equation number 50 is actually the magnitude of the total angular momentum of the electron or the atom. Then you know that when you apply the external magnetic field, what will happen? This vector J shown in equation number 48 will carry out its precessional motion about the magnetic field. Then of course the three components will be formed, that is Jx, Jy, and Jz are created, out of which two components, which is Jx and Jy, will be averaged out to 0 due to the precessional motion of the vector J about the magnetic field, and only one component, which we call as the Jz component, will survive. This Jz component has a relationship, that is Jz is equal to mj into h bar, where mj is the total quantum number, is the total magnetic quantum number of the atom, and h bar is the reduced Planck's constant. The allowed values of mj will be equal to 0, plus minus 1, plus minus 2, plus minus 3, and so on up to plus minus j. So in the absence of the magnetic field, the j values are degenerate values. J values will be the degenerate values. But when you apply the magnetic field, then in the presence of the magnetic field, the J degeneracy will be lifted, and the splitting due to magnetic quantum number Mj will appear. That is, now the energy of the J levels will be going to depend upon the total magnetic quantum number of the atom or the electron, as shown in equation number 51. And you know that there is one magnetic field which we call as BL magnetic field. This BL magnetic field, you know, that arises due to the motion of the electron about the nucleus, and this is what its relationship has been shown in equation number 52. That is BL, that is the internal magnetic field created due to the motion of the electron, is BL, which is mu naught over 2 pi into Z E over m naught r cube into L vector. So PL, which is the magnitude, or which is the vectorial form of the magnetic field created within the atom, is actually directly proportional to the orbital angular momentum L of the electron. So BL interacts with the mu s, which is the spin magnetic moment. Equivalently, mu L interacts with the mu s, called the spin orbit coupling. So you see that when there is a coupling, when there is an interaction between the orbital magnetic moment and the spin magnetic moment, that interaction is called the spin orbit coupling. Basically, the spin orbit coupling arises due to the interaction of the spin magnetic moment with the internal magnetic field BL. But in principle, we can equivalently say that it is the interaction of the spin magnetic moment and the orbital magnetic moment, and we have this relationship derived in lecture number 13 D, in lecture number 12C, which is shown in equation number 52. Then again, you see that when you apply the magnetic field, then due to the interaction of mu L and mu S, then the energy, then the splitting is produced, and that splitting is represented by VLS, which is called the spin orbit splitting. VLS is actually the energy due to the spin orbit coupling, or due to the spin orbit splitting. You can also call it as orbit spin coupling or spin orbit coupling. So this is the energy difference. This is the energy that, or this is the splitting energy due to the interaction or due to the coupling between the orbital angular momentum, orbital magnetic moment and the spin magnetic moment of the electrons. When these two quantities interact with each other, then of course the spin splitting will produce the splitting energy will be produced, which is labeled as VLS, as shown on the left hand side of equation number 54, and the full expression will be equal to minus mu s times BL, and the full expression is shown, which is equal to mu naught over 8 pi into Z E square over m naught square into r cube, and then the term will be L dot S, where L dot S is the dot product between the orbital angular momentum and the spin angular momentum, as shown in equation number 54. The value of the expression equation number 54 then was modified in terms of the quantum numbers. So LS will be equal to A over 2, and within the curly bracket we have J into J plus 1 minus L into L plus 1 minus S into S plus 1, as shown in equation number 59. This expression of the VLS is actually in terms of the quantum numbers, where J is the total quantum number of the atom, L is the orbital quantum number, and S is the spin quantum number. And the value of L, which is called the spin orbit coupling constant, is shown in equation number 56, which is A is equal to mu naught over 4 pi, and then multiplied by the term which is Z E square into H bar square over m naught square into r cube, as shown in equation number 56. And equation number 6 has been also modified in terms of the other parameters, that is A, that is the splitting constant, or you can say that it is A is the fine structure splitting constant, is roughly equal to Z to the power 4 divided by N to the power 3 multiplied by the terms which are L plus 0 term, L plus half term, and L plus 1 terms, as shown in equation number 63. So this was covered in lecture number 3 of this series. This lecture was presented in slide number 12C. Now I am going to present the last lecture of this series, that is the fine structure in hydrogen atom. So the energy of the electron in a hydrogen atom when it is in the nth state, following equation number 3.14, that is equation number 14 of lecture number 3 is reproduced below, which is E is equal to minus half then m naught over 4 pi epsilon naught square, then the term is z square into e4 e to the power 4 divided by h bar square, and then we have the term which is 1 over n square. So I have relabeled this equation as equation number 12.64. We know that here the energy of the electron in a hydrogen atom depends upon these parameters. Then only the principal quantum number n is responsible for the splitting of this energy. So there are no other constants, there are no other quantum numbers which are responsible for the splitting of this energy. Now you see that if you set z is equal to 1, then this will be the case for the hydrogen atom, and representing the energy in terms of the Rydberg constant gives the following equation. So representing equation number 12.64 for the hydrogen atom, and representing the parameters of that equation in terms of the Rydberg constant of the hydrogen atom, the equation number 64 will take the form as given in equation number 65. E is equal to minus R into H into C multiplied by 1 over n square. Again, you can see that this is a short written energy expression for the energy of the electron in a hydrogen atom, which is determined only by the principal quantum number n. So you see that while writing equation number 65, we have ignored the relativistic mass effect. So if you include the relativistic mass change, then following equation number 6.7, Sommerfeld reduced the following formula. Sommerfeld introduced the following formula. So E and L, you see that on the left hand side you have energy. Now the energy is going to depend upon two quantum numbers, principal quantum number and the orbital quantum number L. So E and L will be equal to minus R into H into C into 1 over n square, and then in the square bracket we have 1 plus alpha square over n square, and then in the parenthesis I have n over L minus 3 over 4 plus higher order correction terms. This formula we have already discussed in equation number 6.7, that is in equation number 7 of slide number 6. And you know that here the energy depends on two quantum numbers, principal quantum number n and the orbital quantum number L. So you see that in the relativistic mass change, the orbital degeneracy is lifted. That is, the energy is now going to depend also on the orbital quantum number L, where alpha, which is called the fine structure constant, Sommerfeld fine structure constant, is given by alpha is equal to E square over 2 epsilon naught Hc, and its value, because all these are the constants, if you put the value of the charge of electron, the free space relativity, the H bar, the value of H bar and C, then you will get this value equal to 1 over 137. So this is a dimensionless constant and is known as the Sommerfeld fine structure constant. So you see that in equation number 66, the energy of the atom in a hydrogen atom using the Sommerfeld model will now depend upon two quantum numbers, that is the principal quantum number and the orbital quantum number, and which means that if you talk about the relativistic mass change, if this effect is included, then of course the energy will further be depending upon the orbital quantum number L. That is, we can say that is the orbital degeneracy is lifted, which means that the energy is now going to depend upon the orbital quantum number, as obvious in equation number 66. Due to the spin orbit coupling, and you know that I have explained the spin orbit coupling mean that the spin magnetic moment and the spin that is the orbital magnetic moment mu L and the spin magnetic moment mu S will interact with each other, which is called spin orbit coupling. So due to spin orbit coupling, an additional energy term appears, which is reproduced below following equation number 54, which is VLS is equal to mu naught over 8 pi into E square over m naught square R cube, and then we have the term L dot S, that is the dot product between the orbital angular momentum and the spin angular momentum, as shown in equation number 68. For hydrogen atom, the principal energy term is much larger in comparison with the energy due to relativistic correction and the energy due to fine structure, that is the energy due to the LS interaction as shown in equation number 68. However, the magnitude of REL, which is REL stands for relativistic correction. So energy correction due to relativistic things and ELS, that is the energy due to spin orbit coupling, are comparable. So EREL and ELS, these two quantities, these two energy terms are comparable with each other, but their magnitudes are much smaller in comparison with the principal energy term, which I have discussed in equation number 64 or 65. So the total energy on which, so the total energy of an atom is given by E with the subscripts of N, L, J, which is shown in on the left hand side in equation number 69, and on the right hand side I have summed up those energies. One energy is the ENL, which is due to the Sommerfeld model. So the energy here depends upon two quantum numbers, principal quantum number N and the orbital quantum number L, and then we have the correction due to the relativistic motion, relative motion between the electron and the nucleus. Due to that relative motion we have this correction, which is EREL, and then due to the spin orbit coupling I have the term which is ELS term. So these three energy terms will then add together to give you the total energy of an electron in an atom. And this energy expression is shown in equation number 69. Now the two terms, one is the two terms shown in the parenthesis, which is E due to relativistic motion ERL, and plus energy due to the spin orbit coupling, which is ELS. These two add together give you the fine structure correction, which we label as EFS. So EFS represents the fine structure correction, which is based on the sum of these two energy terms, which was calculated by Dirac and is reproduced below. So you see that Dirac actually combined these two energy terms in another energy form, which is in another energy term, which is given in equation number 70. So EFS, which is the fine energy term, will now be equal to minus En, which is the principal energy term, multiplied by alpha square over n, and then in the parenthesis we have 1 over j plus half, then minus 3 over 4n, where j is the total quantum number of the atom and n is the principal quantum number, alpha is the Sommerfeld free structure for Sommerfeld fine structure constant, and again n is the principal quantum number and En is the principal energy term, which I have discussed in the initial two equations, that is the energy terms that will arise in equation number 64 or in equation number 65. So you see that this energy, this is the fine structure energy term, which the Dirac presented after combining EREL and ELS. So this is now the fine energy, the energy term that we shall be concentrating on, as shown in equation number 70. So here L in the Sommerfeld correction has been replaced by J plus 1/2 in the Dirac fine structure energy term. The fine structure energy term of the hydrogen atom thus depends only on the total quantum number J and not on the orbital quantum number L, as obvious in equation number 70. So you see that we shall replace the two terms EREL and ELS shown in equation number 69 by the energy term shown in equation number 70, derived by Dirac, and is shown in equation number 70. Where the fine structure energy mainly depends upon the total quantum number J of the atom and the principal quantum number J of the atom. Fine structure splitting of the states with n is equal to 1, 2, 3 according to Dirac is shown in this diagram, which I am going to discuss. States with the same L are degenerate. without fine structure. That is, the states L will be single states. They will not further split if we ignore the split orbit coupling. But if you include the spin orbit coupling, that is the fine structure coupling and the formula which is given in equation number 70, then of course the L degeneracy will be lifted. That is, the energy will now going to depend upon the values of L. States with the same J have same energy if Fs is taken into account. Now you see that, let me show you this diagram first. You see that in this diagram, there are horizontal lines, dotted horizontal lines against n is equal to 1, then against n is equal to 2, then against n is equal to 3. These are the horizontal dotted lines, and these corresponds to the energy level of the hydrogen atom, corresponding to the principal energy term in the hydrogen atom, as shown in previous equations. That is in equation number 64 and 65. These dotted horizontal lines are due to energy term shown in equation number 64 or 65. Okay. So these reference lines are given for as a reference. Then you know that let's consider few electrons, that is s electrons. This is the one s electron of the hydrogen atom, one s electron representing the ground state of the hydrogen atom in the presence of the fine structure energy. Then you know that this energy level will be shifted below the actual energy, reference energy level of the hydrogen atom, corresponding to the principal energy term. Then you see that this one electron, this energy of this one s electron will be lying below, much below the principal energy term, principal energy reference line, which is shown in the dotted line against n is equal to 1. And you know that this energy term due to the fine structure will be equal to minus 1.8 into 10 to the power minus 4 electron volt. So the one s electron, if you include this energy term, that is the fine structure energy terms, then of course this will be lying much below the reference level. Then if you consider the second, if you consider 2s electron, you see that here I have written, instead of 2s electron, I have written 2 into s half. So you can simply also write as a 2s electron, because this is a single electron, and you know that for the single electron the value of the quantum number j will be equal to half, because for the s electron the value of L is equal to 0, and only the value of spin quantum number will be equal to half, and you know that j quantum number will be equal to mod of L plus minus half, and if you add there 0 plus minus half will give you the total angular momentum j is equal to 1 half. So 2s half is the second s electron. So this is the 2s electron of the hydrogen atom. So below 1 was the 1s electron. So 1s electron represents the ground state of the hydrogen atom. So this is the first excited state of the s electron of the hydrogen atom, which we call 2s electron. And you know that for the 2s electron, you will notice that its energy is also below the reference energy of the hydrogen atom, represented by delta EFS. And this is the correct energy if you incorporate the energy difference of energy due to the fine structure. And if you consider the 3s electron, that is the electron, that is the 3s electron, that is the second state of the electron in the s state, which I have written as a 3s half. There is a 3s electron, and you will also notice that its energy term is also below the reference level, corresponding to n is equal to 3 level. And you can notice one thing, that the magnitude of delta EFS is maximum when value of n is, when value of a principal quantum number is small. But if you go with the higher values of the principal quantum number, you will see that the value of that the value of delta EFS becomes smaller. And you know that for example, the value of E delta Fs is smaller for the value given for n is equal to 1, and the value for n delta EFS for the principal quantum number 3 is even smaller than in comparison with the value of E delta Fs given for n is equal to 2 and n is equal to 1 respectively for the 2s electron and for the 1s electron. So this was the story for the s electrons. And you see that I have shown capital S for the S electron, because for the S electron, the spectroscopic symbol is capital S, which means L is equal to 0. Now you see that now let's talk about the p electrons. When we talk about the p electrons, it means that the value of the the value of the angular momentum orbital quantum number, that is the value of L is equal to 1. And you know that the terms will be represented by p. So the lowest value for the p is the 2p electron, and the next higher states for the p electron will be the 3p electron. So I have shown in this figure two states of the p electron. One higher state is the 2p electron, and the second higher state is the 3p electron. And you know that this 2p electron has two levels. That is the case of doublet. That is, I have 2p half and 2p3 half, and the energy gap between them, which is the fine structure energy, is also shown, which is equal to 0.36 centimeter inverse. So you see that for this, for 2p3 half and for 2p1 half, the value of orbital quantum number is L is equal to 1. But you know that the L degeneracy has lifted, because we have included the spin orbit interaction, and due to spin orbit interaction, this level, which should be a single level, a single degenerate level, the degeneracy has lifted, and then we have a splitting of that level into two levels, which we call as doublet levels, represented by 2p3 half and 2p1 half, with a separation of the fine structural energy equal to 0.36 centimeter inverse. And you know that these three half and one half are the value of the total quantum number J of the atom. And n and 2 just before p is actually the value of the principal quantum number. And here you will see that the energy of the 2p half and the 2s half are very close to each other. Actually, we cannot make a discrimination between the energies of the 2s half and 2p half. So they are at the same energy level. So let's discuss the 3p electron. In the 3p electron, again, due to, for the 3p electron, you know that the value of the for the p electron, the value of the orbital angular momentum L is equal to 1. And again, this 3p level will again have will have a doublet states, that is 3p3 half and 3p1 half. So p3 half and p1 half will be the doublets level, and this splitting is again because of the spin orbit coupling. Otherwise, it should be a single level. But if you include the spin orbit coupling, then these will be the two levels. That is, the orbital degeneracy is lifted, and then you will have two levels, and the separation between two levels in terms of energy is also shown, which is the fine structure energy splitting term, which is equal to 0.108 centimeter inverse. And you know that if you go with the higher higher values of the principal quantum number, then this energy gap will reduce with the increase in principal quantum number. So you can see the difference of energy, which is which is equal to 0.108 in comparison to 0.36 centimeter inverse. So if you go with the higher principal quantum number, this difference of energy will reduce with the increase in value of the principal quantum number. That is, this difference will reduce with higher states, with higher p states, and ultimately you will see that the difference becomes very small, and approximately require very high precision experimental setups to make a measurement of such fine structure energy terms. Then I have also discussed only one state of the d electron. You know that for the d electron, the value of the orbital quantum number is 2. For the s electron, the value of the orbital quantum number is 0. For p electrons, the value of the orbital quantum number is 1. For d electrons, the value of the orbital quantum number is 2. And due to that one, if we have the value of j will be equal to 3 half and 5 half. Again, these are the two doublet terms, and you see that they are splitted again because of the fine structure splitting terms. If you ignore the fine structure splitting terms, then these levels which I have shown as the doublet levels will be only a single level, and then you see that we would say that for the same L the levels are degenerate. But if you include the spin orbit coupling, that is the fine structure splitting, then of course there will be two doublets terms instead of the single term, that is the L degeneracy will be lifted, and you have the doublet terms. And these but for only the s electron there will be singlet terms because L value is equal to 0, but for other electrons there will be two doublet terms. And for the d terms, you have again d5 half and again d3 half, and the energy gap between them is 0.036 centimeter inverse. And again, in this case, you will notice that the value of the level 3d, that the level 3 that the level d3 half is at the same energy level as the level p3 half. So there is no difference of energy between the values of J, between the same values of J. That is the level D3 half and the level P3 half exist at the same energy level in this diagram. And again, in this lower level, the level P1 half and the level S1 half also exist at the same energy level. But you see that later we shall see that these levels are also separated in energy. That is with the same J value, that is the P1 half and the S1 half, which I have shown to be at the same energy. Later we shall see that there is a difference. There is also a difference between energy levels with the same value of J. And that will be due to Lamb shift, which we shall see, which we are going to discuss in the today's lecture. And also you see that here I have shown that the level D3 half and the level P3 half are also at the same energy level. But in principle, later we shall see that when we shall take Lamb shift into account, we shall see that there will be a difference of energy between these two levels having the same value of J. So you see that this diagram corresponds to the diagram when we take into account the fine structure splitting. So due to the fine structure splitting, each level in the hydrogen atom will be split into two levels, that is into the doublets, except for the s electron. EFS, that is the energy splitting due to the fine structure, is larger for heavier atoms, and it goes as z to the power 2. For example, as obvious in this formula that we have used earlier. So the splitting of the fine structure splitting in equation number 59 depends upon the constant A, and the constant A in turn depends upon the value of Z. But you know that if you take into account equation number 63 in terms of the quantum numbers, then the splitting of constant A goes as to the power Z to the power 4. And in the denominator, you have n to the power 3. So this splitting constant, you know that varies as Z to the power 4. So if you express this EFS in terms of the quantum numbers, you can say that EFS, that is the fine energy splitting, is larger for heavier atom, and it goes as Z to the power 4, as I have just explained, and is easily observable. So you see that fine structure constant varies with Z to the power 4. So for heavier atoms, this fine energy splitting can easily be observed. But you know that I have also shown you that this EFS also depends upon 1 over n to the power 6. Sorry, to the n to the power 3, as shown in equation number 63. So you see that if you go along the vertical direction, that is for higher states where the principal quantum number 1 will increase, then of course the splitting will decrease, as I have shown over here. That is, for example, from this level to this level, the splitting energy will decrease, because with the increase in principal quantum number, the energy difference will decrease. This is what I have explained over here. So it is difficult to find an expression for the energy splitting due to the fine structure for heavier atoms, because for the heavier atoms, it is for the heavier atoms, the atoms are more complex, more having more electrons around the nucleus, and then you see that it is difficult to find out the wave function for such heavier atoms. And of course, the empirical formulas cannot be calculated for heavier atoms, or the analytical expression of the formula for the fine structure splitting for the heavier atoms cannot be calculated because of the complexity of the wave functions involved. Now you see that now I am going to discuss the lamp shift. And the lamp shift, why we are going to discuss the lamp shift? Because here you see that in this diagram where I have included the principal energy of the hydrogen atom along with the fine structure of the hydrogen atom, and I have shown that each line of the hydrogen atom will be split into the doublets. Well, you see that here in this diagram, I have assumed that the level P1 half and the level S1 half, they are at the same energy level. Similarly, I have assumed over here that is the D3 half and the P3 half are also at the same energy level. Similarly, I have assumed that P1 half and S1 half, they are at the same energy level. But you know that in principle there is a difference in energy level between these states having the same value of J, and this was explained by the Lamb shift. So Lamb shift, they reported their work in the year 1947 to 52, and Lamb with Rutherford performed some experiments, and then such experiments are now referred to as simply as Lamb shift. Even the relativistic Dirac theory, that is the fine structure theory, did not completely describe the hydrogen atom, in the sense, because in principle there is a difference between P half and S half states. That is, the same J value will have different energies, should have different energies, which is the same over here, because this picture is due to Dirac, and you see that there is these two levels are at the same energy difference, are at the same energy level, but in principle these levels as observed spectroscopically there is a difference of energies between these two levels having same value of J. This was not explained by Dirac. So even the relativistic Dirac theory did not completely describe the hydrogen atom. They demonstrated the absorption of high frequency microwaves. Now you see that now I am talking about some experimental thing, that they demonstrated absorption of high frequency microwaves from klystron tubes by hydrogen atoms for the observation of small energy shifts and splitting in the spectrum of hydrogen atoms having the same value of J. This way the energy difference, this way the energy difference energy difference between the terms with the same J was observed. So the two terms in the having the same value of J will now be splitted in energy. That is the J degeneracy will be lifted. So this is shown over here in the diagram. The energy difference of the order of 0.035 centimeter at a wavelength of 900 megahertz was observed between the terms 2s half and 2p half. That is between these two terms, 2s half and 2p half. It was observed using microwaves absorbed by the hydrogen atom, and we found that there is a difference between the energy levels. That is the 2s energy level is slightly and that is the energy of the 2s level is slightly different from the energy of the 2p levels. So this was confirmed when the hydrogen atom was made to absorb microwaves at about 900 megahertz, and the splitting and the energy gap of the order of 0.035 centimeter inverse was observed between the s half state and 2s half state and 2p half state. So now this is what I have shown. On the left hand side, I have plotted the wave numbers in centimeter inverse, and on the right hand side I am showing the splitting. So one is the Bohr splitting for the n is equal to 2 state, and you know that there is only one level according to the Bohr, because the Bohr level depends that is the energy in the Bohr level depends only on the principal quantum number n. So there is only one level, and if you include the Dirac, where the Dirac includes the principal energy of the hydrogen atom along with the fine structure energy, then of course that the energy will depend upon the value of J. So we have J is equal to 3 half, for example. For the case of the N is equal to 2, I am talking about the S electron and the P electron, because I am talking about these two level, 2s half level and 2p half level. That is, I am talking about the P level, and also I am talking about the S level over here, and also 2p3 half and 2p1 half, and also 2s half levels. I am talking about these these three levels over here, or due to the Dirac theory. So J will have 3 half value and 1 half value. So you see that for the p electron, the value of the orbital quantum number L is equal to 1, and since there is a single electron involved for the case of hydrogen, so the spin quantum number is always half. So L plus half will give you 3 half value for the p electron. And similarly for the p electron, since there is 1 plus minus half, so 1 minus half will give you the value of J is equal to 1 half. Again, for the p electron, you have two values of J. One is 3 half, the other is 1 half. So let me show you over here. So for the p electron, you have two values of levels. One is p3 half, that is the J is 3 half value, and the other value of J is 1 half. So according to that one, you have two levels, p3 half and p1 half. And you know that for the s electron, because I am talking about a level n is equal to 2 level, and for the n is equal to, you know that when the value of n is equal to 2, there are two values of orbital quantum number L. One is 0, the other one is plus minus 1. So according to the principal quantum number n is equal to 2, the allowed values of L is equal to 0 and plus minus 1. And when you have the 0 value of the orbital quantum number, again the spin quantum number is always half for the case of single electron. So you have 0 plus half will give you s electron, and 0 plus half will give you the value of the total quantum number equal to half. So for the s electron, you have the total quantum number equal to half. For the p electrons, you have two values of the total quantum number J, which is 3 half and 1 half. So for the p electron, you have two states. One is with the 3 half, the other is with 1 half. And for the s electron, you have only one level, which is 1 half. So for the s electron, you have only one level. For the p electrons, you have two levels, p3 half and p1 half. So you see that according to the Dirac, the energy level of the P3 half is greater than the energy of the P1 half. This level is P3 half. This level is P1 half. And also this level is S1 half, because there is no energy gap between P1 half and S1 half, because these are degenerate levels according to the Dirac theory. And you know that the splitting between the 3 half and 1 half is due to fine structure energy included by the Dirac or introduced by the Dirac theory. And you know that when you include the lamp shift effect, then of course this level, which is two levels actually, P1 half and S1 half, they will be split into energy gap. And you will see that the level S1 half is slightly greater in energy than the level P1 half, with an energy of 0.035 centimeter inverse. And so this is according to the quantum electrodynamics, that is including the lamp shift effect. So due to the lamp shift, the L degeneracy which was present over here is lifted, and now the energy is going to depend upon the values of J. So here you see that J degeneracy was present, that is values with the same J have the same energy, but you know that here the J degeneracy is lifted, that is different value of J will have different values, and this effect is called a lamp shift. That is according to the lamp shift, which is due to the quantum electrodynamics theory. You have to include, you would say that the levels with same value of J, that is for example S half and P half, they are different in energy, and here in this case the value of S half is greater in energy in compare with the P1 half. So if you refine the previous diagram, for example this one, then the level S half will be greater in energy than the level P1 half. Similarly, the level 3S half will be greater in energy than the level P1 half. And similarly, the level P3 half will be greater in energy than the level D3 half, but of course below D5 half. Splitting of N is equal to 2 level in hydrogen atom according to Bohr, Dirac and quantum electrodynamics, that is due to the lamp shift effect was presented in the previous diagram. The J degeneracy is lifted due to fine structure. So you see that the levels here are going to depend upon the value of J according to the Dirac. Here the J degeneracy is lifted, because the value of J3 half is greater than the value of J1 half according to the fine structure. The J degeneracy is lifted due to fine structure. Small energy difference with the same J was observed due to lamp shift. So this fine energy difference having the same value of J, the energy difference between two levels with the same value of J is due to lamp shift. Generalization. So levels with the same N and J but different L, for example S1 half and P1 half, are not the same in energy. You can notice for these two terms that is the value of the principal quantum number is the same. The value of the quantum number J is also same, that is 1 half and 1 half in both cases, and the principal quantum number is 2 and 2 in both cases. So N and J are the same for the two terms, but the value of L is different. For example, for the value of 2s half, the value of L is equal to 0, and for this P term, the value of L is equal to 1. That is, the value of L is different. So here I am going to say that the levels with the same N and J but different L are not the same in energy. all S half terms are higher than P half terms in energy equal to 10% of the energy difference between P3 half and P1 half. Similarly, P3 half terms are higher than the D3 half terms in energy by about 2% of the energy difference between D5 half and D3 half. Now you see that I am going to present over here an experiment that will allow you to measure the lamp shift experimentally. I am going to briefly go through this experimental setup and then through the paragraphs that I am going to present in the next slide. On the next page, this experimental arrangement will be explained in greater detail. This is an oven on the left hand side of this experimental setup, which contains a hydrogen molecule, H2 molecule. So we raise the temperature in the oven up to about 2500 degrees centigrade, so that the H2 molecule will break up, will dissociate into atomic hydrogen. And then the atomic hydrogen in the ground states are produced, and the ground state by the hydrogen atom which will come out from the oven is 1s half. So these 1s half electrons are bombarded with the electron beams. When these hydrogen atoms in the ground states are bombarded with the electron beams, then some of them, which is a very small percentage of them, will be excited to the hydrogen, to the 2s level of the hydrogen atom, which has a spectroscopic term is 2s half. So this is the excited hydrogen atom in the 2s state. But you know that this 2s state is the metastable state. So it is a long-lived state. So when these atoms will pass through a chamber which has a tunable microwave resonator, and also we are applying a magnetic field B over there, then of course this hydrogen atom with a 2s half state can be converted, a small percentage of that can be converted into 2p1 half, and also into 2p3 half, depending upon the value of the microwave resonator that we set. For example, if you set the tunable microwave resonator at about 1 gigahertz, then of course you will be able to make 2s half to induce to the value of 2p half, because the 2p half is lying lower in energy than 2s half. So by applying a microwave resonator with a free microwave frequency of 1 gigahertz, you can induce 2s half to a hydrogen level to the level 2p1 half. But if you apply a microwave resonator at a frequency of 10 gigahertz, then you can excite this 2s half to a level of 2p3 half, because the 2p3 half is lying higher in energy than the 2s half level. So you see that microwave assembly over here, or the resonator, which is a tunable resonator, in which we can tune the energy of the microwave from 1 to 10 gigahertz, can produce two versions of the hydrogen atom, that is the hydrogen atom in the state 2p1 half or in the state 2p3 half can be produced either by tuning the microwave assembly to 1 gigahertz or to the 10 gigahertz. Now the question is that what is the purpose of B field? The B field actually finally or refinally set the separation between the two levels. For example, you can see these two levels over here, 2s half level and 2p half level. Because the microwave that you will set up, the energy of the microwave cannot be exactly equal to this difference, because the microwave because in the microwave the value of the wavelength is fixed and cannot be precisely tuned according to the energy gap between 2s half and 2p half. So the magnetic field can be used to adjust the separation between 2s half and 2p half. So that tuning of the magnetic field will allow you to tune the separation between 2s half and 2p half, so that it could match with the frequency which is the so that it could map with the tuned frequency of the microwave, and the excitation or the de-excitation using the microwave could occur to the levels 2p1 half, or the excitation to the level 2p3 half. So you see that once these are produced over here, these levels can decay very quickly. That is, the 2p half and the 2p3 half can decay very quickly to the ground hydrogen state. For example, over here in this state, in this diagram, you can see that when the hydrogen atom is in the 2p3 half or in the 2p1 half, it can decay very quickly radiatively to the 1s level, or to the 1s level of the hydrogen atom. So the radiative decay from the 2p3 half or 2p1 half is very easily possible to 1s state. So what will happen? So for the moment, forget about 2p half and 2p3 half. Suppose that they are not present. What will happen? 2s half will pass through the assembly and will be incident on the tungsten foil, and it will give its energy to the tungsten foil, and the electron will be emitted. This electron will flow in this circuit, and a current is recorded. So when you there is a specific value of the current due to the presence of 2s half. But you know that if some value, if some percentage of 2s half is converted to either 2p1 half or 2p3 half, then of course it means that we are reducing the reducing the percentage of 2s half to reach the tungsten foil, because a part of that one has either been converted to 2p1 half or 2p3 half. So due to reduction of due to the reduced percentage of 2ps half reaching the tungsten foil, the current will decrease, and the decrease in current will indicate that either we have produced 2p1 half or 2p3 half. So a reduction in the current can inform us that either 2p1 half or 2p3 half have been created depending upon the resonator tuned either to 1 gigahertz or 10 gigahertz respectively. So you see that by that one we can find out the energy of the difference between the difference of energy used by the microwave and the B field for the creation of 2p1 half and the 2p3 half. So for example, if we talk about the 2p1 half over here, then of course the energy due to the energy level of the 2p1 half can be measured very precisely using the tunable range of the microwave, and also due to the magnetic field. Due to the precise tuning of the magnetic field, the energy level of the 2p1 half can be calculated. And you know that the energy of 2s1 half is already known to us. So the energy gap between 2p1 half and 2s1 half can be measured. That is the energy gap between the two levels, 2s1 half and 2p1 half, can be measured very precisely. And you know that this is nothing but the lamp shift. That is the energy between the two states having the same value of J, in this case as 1 half and p1 half, and the value of J is 1 half and 1 half, can be measured very precisely. For example, 0.035 centimeter inverse can be measured very precisely in this experiment. So the lamp shift can be measured very precisely and experimentally using this arrangement. Now let me go through very quickly, although I have explained the experimental setup, but I am going to go through the following paragraphs very quickly. H2 molecules are heated to 2500 degrees Celsius, and due to the thermal dissociation, hydrogen in atomic form are produced. The hydrogen in its ground state has a term state represented by 2s1 half. This is the ground state of the hydrogen atom. This atomic hydrogen atom represented by s1 half is passed through or bombarded by the electron beam so that the first excited s state can be achieved, which is represented by 2s1 half. The excited metastable 2s1 half is a small fraction of the total number of H1s half atom, and it is around about 1 in 1 million. So the 2s half which are produced by the bombardment of the electron beam is actually a 1 in 1 millionth of the actual number, which is 1s half. For the time being, assume that the microwave tunable assembly and the magnetic field setups are absent, and that the 2s half atoms reach metal detector, that is the tungsten foil, which ejects electrons and a current is detected. Only the H2s half atoms can make the tungsten foil to eject electrons. There are two possibilities. Either H2s half is induced to de-excite to the H2p1 half with a resonator at 1 gigahertz, or excited to H2p3 half with a resonator at 10 gigahertz. So there are two possibilities. Either you generate 2p1 half or you generate 2p3 half. By controlling the tunable resonator, either H2p1 half or H2p3 half is achieved. So one of them is achieved. Both can decay to the ground state H1s half radiatively and immediately, and the emitted wavelength, if required, can also be measured. But you know that in the historical experiment that I am going to describe, that I have described due to Lamb and Rutherford, in that experiment the wavelength was not measured, and the energy gap was only measured due to using a microwave resonator tunable assembly and the tunable magnetic field. The adjustable magnetic field allows to adjust the energy separation between the levels so as to match with the fixed microwave frequency. Thus, the transition to P2S to 2P can be achieved, that is either from H2S half to H2P1 half, or from H2S1 half to H2P3 half can be achieved. So one of these has to be achieved. When H2P1 half or H2P3 half is created from H2S1 half, they decay immediately to the ground state H1s half. That is due to these P levels. P1 half and P3 half can decay to the ground hydrogen state, which is 1s half, and the number of 2hs half reaching the detector falls in number, and a dip in current is recorded. The value of the microwave frequency along with the magnetic field for the transition from this to this can then provide a precise measurement of the energy gap between between H2S half and H2P1 half. A definite value of this energy gap confers the Lamb shift. So you can also express the previous experimental diagram using this symbolic or schematic diagrams. H2 broken into atomic hydrogen 1s half. This one s half, which is in the ground hydrogen state, through the bombardment of electron beam converted into the first excited state, which is H2, which is the H2s half state. That is the electron is created. That is the hydrogen was created. That is the hydrogen was raised to s to 2s electron state, and 2s electron state means 2s half in spectroscopic symbol. This hydrogen atom in state 2s half will pass through the chamber having microwave, tunable microwave and tunable magnetic field assembly. Now through this assembly, either through this assembly, hydrogen atom in 2p1 half is produced, and this p1 half will decay immediately to the ground hydrogen state, which is 1s half state. And when this reaction occurs, then of course, then 2hs half, number of 2hs half is reduced in number, and this reduced number when falls on the detector, then of course the current is measured. This current will be reduced when this reaction occurs. That is when 2p1 half are created, then a dip in current is measured. And by measuring the dip in current, we can immediately measure the value of the microwave wavelength, and also the tunable magnetic field strength can be measured, and from these two parameters we can infer the energy gap between the 2s half state and 2p s half state s half states. That is the energy gap between 2s half and 2p1 half can be measured when a dip in current is recorded. And the microwave frequency and the tunable magnetic field, from these two parameters, the energy gap between 2s half and 2p half can be measured precisely, which is a lamp shift. Now you see that in the next diagram, that is in this diagram, I am going to represent the hydrogen atom for the states, all the splittings in the n is equal to 3 state and n is equal to 3 and n is equal to 2 state, using a fine structure and lamp shift. So now I am presenting a complete picture of the hydrogen atom for the n is equal to 2 state and n is equal to 3 state, including both fine structure due to the Dirac and lamp shift effect. So fine structure represented by green Fs between states with the same L but different J. So you know that in the fine structure we have the energy splitting for the terms having same J values. For example, notice this one, this figure for example. You will notice that this J value 3 by 2 and 1 half, different J values will have different energy. This is fine structure. And then the lamp shift. So you see that different J. If you have different J's, then of course the values of the energy terms will be different, and the different energy terms will be due to the fine structure. And fine structure means that due to the interaction of the spin magnetic moment and the orbital magnetic moment. And the lamp shift. Lamp shift is actually the difference between states having same value of J, but of course a different L, same value of J. For example, 2s half and 2p half, same value of J, but of course different in energy. This gap, such a gap will be represented by lamp shift. And the lamp shift will be, in the figure, will be labeled by LS, lamp shift. And this is between states with the same J, but a different L. So first of all, I show you the splitting for the level n is equal to 2. So for the level n is equal to 2, the values of the or allowed values of the orbital quantum number are 0 and 1, And then when you have orbital angular momentum 0 and 1, then of course for the single electron the value of spin is always half. That is, the spin quantum number is always half, and the splitting is shown, which is 2p1 half, 2s1 half. You know that this is now lamp shift, and the energies are shown in centimeter inverse. So 0.0353 is in centimeter inverse, and the energy of the 2s half level is greater than the energy of 2p1 half, and the energy separation between 2p3 half and 2p1 half, that is the same L case, is the fine energy difference. So the energy difference for the terms which is p3 half and p1 half having different values of j but the same value of L, because the value of L is equal to 1 for p3 half, the value of L is equal to 1 for p1 half. So for the same value of L but different values of j, the values is called fine structure. And for the same value of j but different value of L, for example, the value of L is equal to 0 for S state, the value of L is equal to 1 for P state. So for same value of j but for different value of L, it is a lamp shift. And these values are shown in centimeter inverse. So similarly, for n is equal to 3 level for the hydrogen atom, I have shown these states. This is 3p half state, above which is a 3s half state. So 3s half state is higher in energy than the 3p half state. And this p half state has its corresponding counterpart as a 3p3 half state. And this 3p half state, and then you know that for n is equal to 3, we have the d electron also. Because when n is equal to 3, the allowed values of the orbital quantum number are 0, 1, and 2. And when you have the value of 2, then of course the d states will also appear. So the two d states, because the doublet will appear for the case of hydrogen atom, the two d states are 3d3 half and 3d5 half. So d3 half and d5 half are the two doublet terms due to the d electrons. And due to the p electrons, we have two doublets which are p3 half and p1 half. And you know that for the s electron, we don't have the doublet, we have only the singlet. And on the singlet level is shown, which is s half. And you know that 3s half is higher in energy than 3p half. And the phase and the lamp shift between them is shown to be equal to 0.0105 centimeter inverse. Then you know that the energy gap between P1 half and P3 half is actually the fine structure energy gap, which is shown to be equal to 0.1082 centimeter inverse. And you know that the energy gap between D3 half and D5 half having different values of J but same values of L, the energy gap between D3 half and D5 half is the fine structure energy gap, which is 0.0361 centimeter inverse. Here I have shown that the P3 half is actually very close to D3 half. And you know that this measurement was, although P3 half is slightly greater than D3 half, and the energy gap between them is not available at the time the experiment was performed. So I have shown these two levels at the same energy gap, at the same energy level, but in principle, P3 half is slightly greater in energy than the D3 half level. So you see that I have shown these levels for the hydrogen atom for n is equal to 2 level and n is equal to 3 level, including both fine structure and lamp shift. Now in the next slide, I am going to show you the structure of the H alpha line. You know that the H alpha line is produced when there is a transition from the principal quantum number 3 to the transition made to the principal quantum number 2 in the hydrogen atom, then H alpha line is produced. But now in the presence of the fine structure and the lamp shift, which I have discussed in the previous diagram, now the transitions are shown over here between the level n is equal to 3 level, and you know that n is equal to 3 level has these levels: p1 half, s1 half, p3 half, d3 half, d5 half. These are the levels corresponding to n is equal to 3, and the levels corresponding to n is equal to 2 are p1 half, s1 half, and p3 half. These are the n is equal to 2 levels in the hydrogen atom according to fine structure and according to lamp shift, and the transitions have been shown. You can confirm these transitions by yourself that these transitions are correct. This red transition indicates that it is the transition between the P1 half and D and P3 half. Sorry, and D3 half. So it is the transition. The transition shown in red is due to the transition between P1 half and D3 half, because both satisfy delta L is equal to plus minus 1 and delta J is equal to 0 plus minus 1. And the other transitions have also been shown. All possible transitions have been shown. And you know that all these transitions satisfy the two selection rules. These are the optical transitions. That is, a wavelength will be emitted when the transition occurs. And these transitions follow delta L is equal to plus minus L and delta J is equal to 0 plus minus 1. And these are, you see, that 7 in numbers. So H alpha line is actually constituted by 7 wavelengths. The magnitude, the strength of these one, the more intense line means that the probability of those lines are higher. Transitions from n is equal to 3 to n is equal to 2 states in hydrogen atom, including fine structure, higher intensity and lamp shift. Higher energy, higher intensity is indicated by the thickness of the lines. So you see that I have shown the transitions between these levels from n is equal to 3 to n is equal to 2. You know that before that, when we started the course on the hydrogen atom, H alpha line was only a single line. But now H alpha line consists of 7 lines, as I have shown these 7 transitions. And these 7 transitions have been plotted in this diagram. So actually this is the structure of the H alpha line of the hydrogen atom at room temperature. This is a separation between two lines is due to lamp shift. Because if there is no lamp shift, then this would be a single line. This is what you can confirm from the previous diagram. So I have shown actually 5 over here, but in principle there are 7 lines. 2 lines have not been shown. The line's width and their spectral resolution is determined by the Doppler width. So sometimes the Doppler width is large and the line and the resolution is not possible, especially between those lines which are very close to each other in energy. They cannot be resolved because of the presence of the Doppler width. Now, if we use a spectroscopy setup which is free of a Doppler free spectroscopy, then of course we can measure those wavelengths also precisely, which is shown over here. So you see that in this is again the same H alpha line of the hydrogen atom, but due to Doppler free spectroscopy, 2 weak lines have been omitted. Again, I have not shown the 2 weak lines over here. The saturated absorption using the dye laser allows a resolution of the individual components. So you see that saturated absorption using a dye laser system can be used to precisely measure these lines. So this is the structure of the H alpha line with and I have not shown the two weak lines over here. So five lines, so five major lines have been shown. So again, you see that this is again H alpha line, which differs from the previous over here in the sense that here, due to the Doppler effect, we cannot resolve, we cannot give a detail of the spectrum, but here we can give you the detail, further detail, because here this spectrum is obtained in a Doppler free spectroscopy. So you see that again, this is a setup. But here this is a setup for the H for the lines from the helium atom. So let me first of all read the diagram, read the caption. Lamp shift and fine structure of the helium atom. Fine structure at 1640 angstrom. 7 components were observed. 1, 2, and 3, 4 will be unsplit without lamp shift. That is, if you don't include lamp shift, then 1 and 2 and 3 or 4 will merge together and will show a single peak. Fine structure and lamp shift can easily be observed for heavier atoms, even in the presence of Doppler broadening. So you see that even the Doppler broadening is present in this spectrum, but you know that since this is the heavier atom, helium atom heavier than hydrogen atom, so you see that we can still be able to identify these 7 wavelengths. 1640 is due to the fine structure, and the other lines are also shown over here. Quantum electrodynamics. Quantum electrodynamics has dealt previously with the emission and absorption of light quanta in atomic transitions. To explain Lamb shift, quantum electrodynamics had to assume that the electrons in an atom were continually emitting and reabsorbing light quanta, apparently violating a conservation of energy. But of course, under these assumptions, we have reached up to the calculations of the lamp shift. So you see that I have explained. It took me 4 lectures to give you a complete description of the hydrogen atom in order to explain the fine structure of the hydrogen atom. And before that, I have to develop a theory. I had to develop a theory for orbital angular momentum, orbital magnetic moment, and related parameters. And similarly, I had to develop the theory for the spin magnetic moment, spin angular momentum, and spin magnetic moments, etc. And the application of the applied magnetic fields and the responses of those quantities in the presence of the applied magnetic fields, both pure orbital cases and the pure spin magnetic cases and the mixed cases. And then you see that I developed the theory to explain the fine structure, and then later on the lamp shift experiment, for example, in the 2 days experiment, I concentrated mainly on the lamp shift. The lamp shift was explained, and finally I have explained the H alpha line of the hydrogen atom using including the effect of fine structure and lamp shift. So in the last 3 lectures covered in 12A, 12B, 12C, and in the 2 days lecture, which is 12D, I have explained fine structure and lamp shift in much greater detail, and this provided us the opportunity to explain the H alpha line of the hydrogen atom. So this is the end of slide number 12D of the course on atomic and molecular physics.